Okay, y'all, this is the last video for chapter 18, and then there'll only be 2 or 3 for chapter 19, and then we're done with the semester. It's gone by super fast. So this part of chapter 18 is also going to go by super fast, which is good. So we're going to talk about the relationships between Gibbs free energy and other things like K, the equilibrium expression. Okay, so just remember state functions. That's when we talked about this in chapter 9 with delta H. That's a state function is when it doesn't matter how you get there, you still have the same starting place and the same ending place. And I like to think of this as traveling. Okay, so maybe we're going from Texas to Florida, and I would personally prefer to fly because that's a long drive, and I've driven many, many times to North Carolina from Texas, and it's just a really long drive. So if I can fly, I'm flying. Obviously, now we're not flying, but normally I would be all about the flying. But my husband, on the other hand, loves road trips. He likes to see things. He didn't make it out of Texas a lot as a kid. And so now that we've been married, we're trying to see more of the states and get him that experience that I got growing up. And so he would rather drive. And while it takes way, way, way longer to drive there and with all the stops and checking out all the fun things, it's a different experience, but we still get there. So that's what a state function is. It doesn't matter what way you go, but you still get from your starting point to your end point, and it's the same starting and ending point. Okay, so when we have state functions, some things can happen. So if you reverse a reaction, the sign, so the plus or minus, also flips. Okay, also, if you multiply a reaction by some factor, you're also going to multiply delta G. Okay, that's it. That's all we're doing. Multiplying the reaction, multiply delta G, flip the sign if you flip a reaction. All right, so this is Hess's law. Hopefully y'all remember. If you don't, it's going to be a very fast learning curve. So what happens with Hess's law is we're given sets of equations, and we're trying to get those sets of equations to look like an overall equation that we don't have. Okay, so we have values for all of these other delta G reactions, but we're looking for that top one, but we don't have it. So we need to manipulate those bottom ones to make it look like the top one. All right, I personally like to start with the most unique thing, which I would say is propane. Okay, and the only time I see propane is in this first reaction. However, it is on the wrong side, which means I need to flip it. So I'm going to rewrite it, and I'm going to flip the whole reaction. 3 CO2 plus 4 waters yields, that's a real arrow, propane plus oxygen. And remember, my sign flipped, so it's now positive, and it was negative. Okay, then we go to the next most unique thing. This one just happens to go in order. I see carbon here. However, carbon's not the right amount. On the reaction, I need it to be 3, but on our reaction we're given, it's only 1. So I'm going to multiply this whole reaction by 3. So I've got 3C plus 3O2 yields 3 CO2. My delta G is now negative, but I'm going to go ahead and multiply it. And I get negative 1,183.2. Hopefully y'all can see that too. All right, then I see H is here. H is in my third reaction, but it's not the right number. Again, I've got to multiply it. So I've got 4H2 plus 2 oxygens yields 4 waters. Delta G, I'm gonna pull this over just a little bit. Negative 1183.2 delta G. So I'm gonna multiply delta G by 2. And I get negative 194.2 Sorry, 114.2. I don't know what I was thinking. Okay, once you have manipulated all of your reactions, we start crossing off what's the same on both sides. So I'm going to see, oh, that's definitely not what I wanted. I was hoping to see if it would let me change the color, and it is. Okay, so I need to cross out what's the same on both sides of the arrow. It doesn't matter which reaction it is. As long as it's on opposite sides, we're good. We can cross it out, just like in math class when we cross out the x's that are the same, or the y. Okay, I've got 3 CO2, 3 CO2. And look, I've got 3 plus 2, so that's 5, and that'll cross out with this one. So left, I have 3 carbons plus 4 hydrogens to make our propane, which is what we were looking for at the top. So once you've got the right reaction, we just add. That's what I did to get that new reaction. We add our values. And I get negative 23.4. And remember, our unit up here is kilojoules, so I'm going to write kilojoules. Okay. It's fairly easy, but you need to make sure you know what's going on. All right. So it's going to walk us through all of it. Negative 23. There's one more. If you need help with Hess's law, please let me know. There may be one on the test. Okay, so what's free about Gibbs free energy? That free energy is the maximum amount of energy released from a system that's available to do work. Okay, and so for exothermic reactions, some of the heat released as a result of the change in enthalpy, it goes into the entropy, so it's not available to do that work. Even some of this free energy is generally lost to heating up the surroundings, which is very common. Okay. And then this is just a graph. I'm not overly concerned about this. Just remember, delta G being negative is spontaneous. Delta S being negative is not spontaneous or unfavorable. And then when delta H is negative, we're exothermic. Okay, so here's an example of real things losing heat to other processes like the environment. Okay, it's very common we're losing heat, especially to the environment or the motor's doing work, and so it's going to that instead of just being processed through the current. All right, so we will see some non-standard conditions. Really, we're going to focus on this bottom one. I don't love my color choice now. This one, okay, where delta G is equal to negative RT ln K. And that ln is the same ln from kinetics, so it's just that natural log. Make sure temperature's in Kelvin, as we've been doing. And then also, this R value is not the pressure R, but the energy R. Also, it is important to note that our unit here for R is in joules, not kilojoules. So when we calculate it this way, our G is going to come out in joules. And then if it asks for kilojoules, you'll have to convert it. This unit, again, is very specific, and it focuses on, do you know what unit we're talking about? Okay, so just make sure you do. All right, so they're going through pressures. That's fine. We're just going to walk through it. We walk through our Q because we need to know what Q is. Oh, this is under non-standard conditions. I'm not going to ask any that are like this. Okay. I want one with K. So, and I call this equation the Ratlink equation just because it kind of looks like that. Also, it makes it easier to remember. Okay. So remember, when K is 1, G is 0. And we've talked about that. But when G is negative, which is our spontaneous, K is greater than 1, and so it's moving in that forward direction. If G is not spontaneous, that means it's moving in the reverse direction, and then K is less than 1. Okay, so it wants us to use free energies to calculate it. Once we've got this Gibbs free energy, it wants us to calculate the equilibrium constant. So this is where we're using the Ratlink equation, RT ln K. And remember, the unit for R is in joules, so I need to do 2,800 joules is equal to negative 8.314 times 298 times ln K. So then 2,800 is going to get divided by negative 8.314 and by 298. I get ln K is negative 1.13. Okay, and just remember the opposite of ln is E, so I have K is 0.322. Okay, so that's our less than 1, which does add up because our Gibbs free energy is positive. It's not spontaneous. All right. We can do one more. This one we're finding delta G. So I've got delta G is equal to negative 8.314 times 298 times ln K, which is 81.9. And I get negative 10,915 joules, which is negative 100 or 10.9 kilojoules. Okay, so just remember, normally we say that Gibbs free energy is in kilojoules, but when you use this equation, it comes out in joules, and then you need to convert. All right, this is just relating the two equations from that Big Mama equation with enthalpy and entropy with our K. All right, I would go through G. So I would use this information to solve for G, and then I would plug it in to solve for K. I don't use this big convoluted equation. Okay, I just use the two and I do them separately. That's it. Y'all have a great day.